do then is go back to sharing. Okay, I'm assuming everybody can see those slides. So I'm not going to speak to the next 3 or 4 slides. They were just a summary of what we talked about and also kind of what we've actually had questions on. So the whole issue to do with the rheological simplicity, time, temperature, position, shift factors, master curves, etc. The whole issue to do with how the black diagram represents that fingerprint and that smoothness of the shifting. We've talked about that. We talked about the compliance stuff. Again, I'm just repeating that, and obviously the aging stuff as well. And then finding the modification stuff. And again, there is a paper. I was amazed when I looked at this, when I was putting this together over the weekend. This is over 20 years ago that we actually published this particular bit of work on using black space to do those things, fingerprint the binder, ID, compliance areas, etc. So we have moved on, and there are 3 main areas that I think are extremely important at the moment, and where black space diagrams give us such a useful tool in terms of understanding our material behavior. And the first one is to do with damage and healing. So a big topic area at the moment in terms of research, in terms of trying to understand our materials. We know material fails in terms of being damaged under loading, under environmental conditions, temperatures, etc. But we also know that there is this great ability of the material to heal, to self-heal. And it's that balance, or at least the combination of those 2 effects that are now starting to become extremely interesting to try to understand in terms of research activities. So a black space allows us not only to look at that, but also to try to understand some of the other physical phenomena that occur during these tests. And so there are different things that are happening in addition to simple damaging or fade of the material and healing. And the first one is nonlinearity, which we talked about a little bit in terms of the DSR testing. The second one is self-heating or self-cooling, because again, as you stop the test, as you have a rest period possibly, or if you delay the application of your loads, there's a possibility for the material to actually self-cool rather than to be self-heating during loading. There is the thixotropic effects that we talked about in terms of steric hardening and changes that happen that may or may not be reversible. And then, of course, there's obviously damage. And I think it's important to appreciate that trying to understand all of those at the same time in terms of our analysis becomes extremely complicated, especially if some of the phenomena are reversible. Some of them are producing potential biasing effects in terms of the data. So this is an example of, and it looks very complicated, but it actually allows us to see a number of different things at the same time. This is some of the work that was done by the group at ENTPE, University of Lyon, where they are looking at the damaging effects. So they're looking at the change of the modulus and the change of the phase angle for an asphalt mixture. And they are measuring not just those changes. So as the material damages, just to give you an illustration, it will start to damage and its modulus will decrease. So you'll have a downward spiraling of the modulus. And as we showed with the linearity data that I showed you earlier on, we would see an increase as we damage the material in terms of an increase in the phase angle. So remember, this is an asphalt mixture, so the phase angles are considerably lower than what you had seen for the binders. I'm going to go to the next slide, because the next slide actually gives me a chance to actually show the different mechanisms. So the first one is a heating effect. So what's happening is, as we test the material, we know that the direction that will change due to heating will follow that particular red dashed arrow line. We also know that there will be an effect of non-linearity. So if you look at the bottom here, the testing has been done at 4 different strain levels in terms of the testing, and therefore we are potentially moving away from a linear behavior to a non-linear behavior, and that is shown by a slightly different direction. So once we can capture those directions, and we can do that by doing the test with a very, very small number of load applications, so we're not damaging the material, we're simply looking at non-linearity, or we can look at the heating just by looking at one particular strain level, we can start to distinguish and differentiate those different types of behavior. So I don't want to go into a lot of detail, because again, this is probably beyond what we want to be talking about today, but this is a very useful tool for us now to use the black space to start to identify different types of behavior or different types of physical phenomena that are occurring that potentially are masking some of the effects we are seeing in terms of damage and some of the effects that we are seeing in terms of healing. The next area, and I've included 3 different aspects of that, is looking at using black space to understand fracture behavior, or in terms of fracture susceptibility. And I've given you 3 different areas here that are, I think, very important for us in terms of understanding the behavior of the material, but also obviously using black space. So the first one is thermal cracking. And you think, well, thermal cracking is really based on tests that are not done necessarily with the DSR, but usually with the bending beam rheometer, and where we look at the 2 parameters of stiffness and the M value rather than a complex modulus and a phase angle. But again, we can, through data conversion, interconversion of the rheological profiles using probably discrete spectrums, we could actually translate that to complex modulus and a phase angle. In other words, a black space data set that can allow us to understand some of the issues to do with thermal cracking. So I'll show you a diagram, or a couple of diagrams in a second. The next one is durability cracking, and where we've had introduced the Glover-Rowe concept, or Glover-Rowe parameter, point parameter, which is all based around the black space diagram. So that's where the black space diagram is basically the building block for us to actually use that Glover-Rowe parameter to understand durability cracking, aging effectively, in terms of how it affects our materials. And the last one is fatigue cracking. And again, it seems strange that we could use a black space diagram to look at fatigue cracking, particularly as this is a slightly different mechanism to what we would normally determine using the DSR in terms of rheological profiles. But again, I'll show you a quick graph of how we could use that, and potentially how we could use a black space diagram as a specification, or at least a map, if you like, in terms of performance. So let's start by looking at thermal cracking. I said basically this is the data usually generated using the bending beam rheometer. In this particular study, we've got data from binders that have been recovered from field sections. So this is real data from the field. We've just recovered the binder. And then the testing that was done was the BBR test, where we looked at those 2 different parameters, the stiffness and the M value. And if you want to think about the stiffness, obviously it's an easy concept for us to understand as engineers. M value is more about stress relaxation, so some kind of mechanism to dissipate the energy in the system. So we want to have a higher M value and a lower stiffness ideally. And you can see in this diagram, we've got 0, medium, low, and high, and that refers to the observed field cracking of those particular sections of material. So if we look at the 0, we've got low stiffness, high M values in terms of those yellow squares. That's good. In terms of low, slightly lower M values and slightly higher stiffnesses, but still within that upper left-hand quadrant where the behavior is going to be good. And then we go to the medium, slightly further shift, and we go to the high cracking field sections. We can see the binder that's been recovered in terms of that plot. And again, this could be thought of as a pseudo black diagram because we're plotting 2 parameters together. But in terms of the stiffness and M value, we're in this bottom right-hand quadrant. Not a lot of stress relaxation possible because the M values are too low, and very, very stiff or very brittle response. So we can take that data, and through a very clever discrete spectrum interconversion type approach, we can shift that data or convert it into G star and phase angle, where effectively G star value of 111 megapascals and a phase angle of 26.2 degrees is equivalent to exactly the same M value of 0.3 and the stiffness of 300 megapascals. And now we have a black diagram. Again, we've got our modulus on the left-hand axis, the vertical axis, phase angle on the right axis. And what we've got here is those 4 different materials. 0 cracking, we can see straight away much higher phase angles, much lower complex modulus. So in other words, much better conditions in terms of resisting cracking, all the way to the high end where we've got our behavior in the top left-hand quadrant here, high stiffnesses, but the phase angles are now a lot lower. And the phase angle can be seen not just as a viscoelastic balance, but as some means, again, of dissipating energy, of somehow getting a system to relax a little bit. And again, these values correspond to a Glover-Rowe value. And again, I'm going to show you a Glover-Rowe plot in a second. If we take that data, that basically corresponds to a Glover-Rowe value of 184 megapascals at a particular frequency, and obviously the temperature corresponding to the cracking temperature of the road. I said I'll talk about Glover-Roe, talk about durability cracking. Just a little bit of background. The Glover-Roe point parameter is based on, I guess, initial work that was done by Charles Glover in terms of ductility and how ductility can link to cracking performance. It's just basically taking those same concepts, except we are changing some of the parameters. We're using complex modulus and phase angle at a different frequency and temperature. But again, it's the overall concept. If we can have a nice free-flowing ductile material, we can possibly resist the influence of durability cracking or age cracking. Again, the graph allows you to represent a number of different, I guess, boundaries. There is a limiting value of 180 kilopascals. It's like a warning limit, and then a significant cracking limit at about 600. So if I show you what the graph looks like, what we have is the black space diagram, modulus against phase angle, where we've got our two limiting criteria. If we're below the 180, we're in a safe zone, no block cracking or no durability cracking. If we are above that, we are in what we call a block cracking or durability cracking issue area. And we can then start to look at how our binders behave. So these are three different types of bitumen. They've been aged from an unaged condition, 0 hours PAV, through to 1 PAV, 2 PAV, and then 4 PAV aging, with the standard PAV aging protocol being 20 hours. And we can see that as the binder becomes harder and stiffer, which obviously would benefit some properties for our road materials, it goes into a region where it is starting to become susceptible to cracking. And so that black space diagram and the Glover-Roe parameter, very quick indication of how we can understand the performance of our material or the distress mechanisms. We can either use Glover-Roe parameter for mixtures and use black space diagrams for asphalt mixtures, slightly different temperature frequency combinations compared to what we used previously for the binders. But again, we can compare the material in an asphalt mixture in terms of its susceptibility to cracking, durability cracking. And I've got this graph. This is actually binder data. So although this is linked to mixtures because these are recovered binders that have been subjected, obviously, to aging in the field, but also the green, sorry, I'm looking at the wrong graph here, the red aging going to the top. But I've also included some rejuvenation effect where we've taken the aged binder and we've effectively added a rejuvenator. And we've shifted that rheological profile in that particular black space from the left-hand upper corner down to the bottom right-hand corner. So again, we can put in our pass and fail crack onset and significant cracking Glover-Roe parameters, the 180 kilopascals and the 600. This is slightly outdated. It actually should be 600, not 450. That gives us indication of how close we are to the cracking. Last slide, the performance limits in terms of behavior. This looks extremely complicated, and I'll go through this quite slowly. I'm conscious of time, though, but what we've got here is a graph that's been put together by Jeff Rowe. This was presented at the CAPSA conference just before COVID struck. So it must have been October, November 2019, where we've got not just the Glover-Roe parameters in terms of durability cracking. So they're the two lines, the 600 kPa and the 180 kPa in terms of durability cracking, in other words, aging cracking. But we've also got parameters. If we go to the top here, we've got this green line, which is defined as the thermal cracking. If you remember the graph that I showed you where I had converted the BBR M value and the S value to a G star and a phase angle value, that corresponded to a G star value of 111 megapascals, which was equivalent to the 300 megapascals for the BBR value, and a phase angle of 26.2, which corresponded to the M value of 0.3. If we took that value, we could work out what the Glover-Roe parameter is for that particular value, which is 184 megapascals, and then we could produce that graph there. And so that's a thermal cracking line. So where this was durability cracking for aging, we now have ability on the black space diagram to actually have a performance requirement for thermal cracking. If our material is below, it passes. If it's above that green line, it will fail. We can even include the fatigue parameter. So this is the fatigue parameter that was taken from the SHARP study, which was a loss modulus of 5 MPa. Again, we can plot that on the Glover Road parameter at different phase angles and complex modulus combinations to give us that fatigue line. And again, if we're above that fatigue line, in terms of if we're concerned about fatigue cracking, our material potentially would fail, or at least be in a band where we would indicate we need to be very careful about fatigue cracking. If it was below, it would pass. And then at the bottom here, we've included the permanent deformation parameters from the SHARP or the superplate study. One of them for the unaged material and one of them for the aged material. And again, if you look at the top here, for the unaged material, we've got a limit of 1 kilopascal. And for the aged material, 2.2 kilopascals. Remember, this was the G star divided by sine delta parameter, or the one over the loss compliance. And again, very clearly, if we are below that value this time, the material is susceptible to permanent deformation or flow failure, rutting failure. And if we are above it, then we are in a pass region. And so all of a sudden, we've got a black space diagram that effectively is mapping all the different mechanisms that we would experience on our road: rutting, fatigue cracking, thermal, temperature-related cracking, and durability or age cracking. So I'm going to leave it there. There is one more slide in terms of a fingerprint. This is just very similar to what I showed you with the conventional binders. In this particular example, I've got a 7100, and which you can see over here, a nice smooth transition from high stiffness and low phase angles to low stiffness and approaching 90-degree phase angle. I've then got two different types of modified binder. One is an SBS, and one of them was a rubber modified, so a crumb rubber modified wet process material. And then I've got two of these synthetic binders that we've made, a methyl acrylate and an ethyl acrylate. And again, you can see that they have been transitioned through the fingerprint of the black space diagram. So I'm not going to do the summary. You can all read yourself, and you will get a chance to obviously look at these presentations. And I will go to my last slide and thank you again for giving me this opportunity to talk today, and obviously happy to answer, if we've got time, any further questions. So I'm going to stop sharing. Thank you very much.
Thanks, Gordon. Absolutely brilliant way to finish that. I mean, we've been working with our task force specifications within Eurobitumen, trying to make input into the next level of specifications, and that the last slide particularly